Hello everyone. In today's video, we're going to be taking a look at some mechanisms of some of the more common acid-base reactions that you might see in organic chemistry. So without wasting any time getting started, let's take a look at our first reaction. So the first reaction that I want to look at is we're going to look at the reaction of a carboxylic acid with sodium hydroxide. Now I have these drawn out separately, especially the sodium hydroxide, because when in solution, sodium hydroxide will typically exist in its ionic form. So sodium will carry a plus charge, and then our OH will carry a negative charge. And then I drew out our carboxylic acid OH group, and you'll see why I did that in just a second. And so when we're talking about mechanisms, remember that when we draw our curved arrows, these arrows represent the flow of electrons. So we need to show the flow of electrons from an area of high concentration to an area of low concentration. And in acid-base chemistry, we typically see the flow of electrons in conjunction with the transfer of a single proton. And you'll see going throughout these mechanisms that is typically the case. So with this mechanism, again, our base is sodium hydroxide, but the reacting portion of our base is that negative OH group. And so that is where our highest electron density is. And so those electrons are going to be used to attack the proton of our carboxylic acid. The bond between the OH on our carboxylic acid is going to break and shift over to our oxygen to give oxygen another lone pair. And then if we draw out our products, we will see that our products are going to be that oxygen with the negative charge, and then the sodium from the sodium hydroxide is going to be our counter positive charge. And then when OH attacks another proton, that gives us water. So I'll draw it this way so we can see where it came from. And we get this H is now this H on the H2O. So we get the formation of water. And in a lot of acid-base chemistry, you do get the production of water. However, it's a little more rare when looking at organic compounds, but it still can occur. All right, so let's move on to another example of acid-base reactions. So with this compound, I'm going to be using a compound known as pentolithium. And what pentolithium is it's essentially a pentane chain with a negative charge on one of the terminal carbons, which then has a counterion of the lithium, like so. However, in most cases, this is just drawn as a direct bond to the lithium. And then for our other compound, we're going to use ammonia. So ammonia is NH3 with a lone pair. But I'll draw this out because in order to do the mechanism, we need it drawn out a different way. And you'll see throughout organic chemistry that tends to be the case. The typical way of drawing a compound is not the way you need it drawn in order to show the mechanism, so you have to redraw it. So we have NH3 with a lone pair. Now in this case, if we think about the idea that a base typically has a negative charge and is looking to attack a proton, and then acids are typically there to give up a proton. In this case, our pentolithium species is going to be acting as the base because we have that negatively charged carbon and that lone pair. That lone pair will be used to attack one proton on the ammonia. And then that NH bond breaks. Similar to when an OH bond breaks, the NH bond breaks and the lone pair will move to the nitrogen. And then when we draw out our products, we now have a neutral pentane because that negative charge was used to form a bond to a hydrogen. And then we will get a negatively charged nitrogen that has two lone pairs. But then we have that lithium still, so that lithium will now be the counter ion for the negatively charged nitrogen. Okay, let's go ahead and move into another example. So in this example, we'll be using a base that is a very common base in organic chemistry. However, coming just from Gen Chem, you might not recognize this as a base. So let's get into it. So for one of our reagents, I will draw this furan with a positively charged oxygen. And then we will use a compound that looks similar to benzene. However, we have one nitrogen in the ring, and that compound is called pyridine. And pyridine is that common organic base that I was talking about. This compound is often used to deprotonate other compounds. And if we remember back to our relative acidities and understanding how we determine relative acidities, we know that a positively charged oxygen really wants to be neutral, so that proton can easily be given away. And so the lone pair on the pyridine is going to be used to take that proton, and then the bond between the hydrogen and the oxygen will break, and that lone pair will go to the oxygen. And then we will get our products. We'll get our neutral furan molecule, and then we will get a protonated amine, or pyridine, excuse me. Protonated pyridine with a plus charge on the nitrogen. Now the reason we're okay having the plus charge on the nitrogen instead of the oxygen is if we think back to the periodic table with the electronegativity trends. So we have carbon, nitrogen, oxygen, and fluorine. And again, this is increasing electronegativity, or E-neg. So if we think about our periodic trends, we can see that oxygen is more electronegative than nitrogen. Therefore, that oxygen wants to be neutral more than the nitrogen does. In fact, we call nitrogen electropositive, which means that nitrogen is okay to carry a positive charge. It's more stable carrying a positive charge than oxygen is to carry a positive charge. So that's why the positively charged pyridine is okay. Okay, so let's look at yet another example. So for this one, we will use cyclopentane with a chain and an alcohol group at the end of the chain. This compound, if we think back to naming, would be 2-cyclopentyl ethane 1-ol. So again, our numbering would be 1, 2 for our ethane chain. But we won't worry about naming for this video. For this, we're focused on the acid-base chemistry. So for our base in this reaction, we're going to use a compound called sodium hydride. Now, sodium hydride is another base that's often used in organic chemistry. This base cannot work around water. Water will neutralize this base very rapidly and very violently. So when using sodium hydride, you have to make sure you are using dry conditions. You're using typically aprotic solvents, so solvents that do not have any free protons. And we'll go ahead and draw this proton out. Anytime we see a carbon chain and we're doing acid-base chemistry, it's safe to assume that if the alcohol group is the only functional group on that chain, that's where acid-base chemistry is going to take place. And now, looking at the sodium hydride, again, our sodium will have a positive charge, and our hydrogen is actually going to carry a negative charge with a lone pair. Now, this is abnormal. We don't normally see this in organic chemistry, but in this case, hydrogen is the negatively charged species, which means that hydrogen is acting as our base. So that hydrogen will be used to attack the proton of the alcohol, and that alcohol bond will break, pushing the electrons over to the oxygen. And if we draw out our products, we will get a negatively charged oxygen with our sodium as our positive counterion. And then when we have a hydrogen attacking a free proton, we're going to get H2, or hydrogen gas will be eluted. So sodium hydride, it's safe to work with, but because of this production of H2, we have to be careful because it is producing a flammable gas, so it does have the potential to react a little more violently than some other bases that you might use. Okay, and moving on to our last two examples, we're going to be using two other commonly used bases in chemistry, starting with one known as sodium methoxide. So we'll start out with a dione. So a dione is a name given to a compound that has two ketones. So we have ketone functional groups, two of them. We have a dione. Just like with two alcohol groups, we have a diol. So we'll call this a dione. Okay, and then as I mentioned before, our base that we're going to use is sodium methoxide. So we have sodium positively charged, and then we have methoxide. And methoxide is just OCH3, so an oxygen with a methyl group. Now, when looking at this dione, there are two types of protons in this molecule. We have the protons on this center carbon, and then we have protons out here on the methyl groups at the end. So when thinking about which protons we're going to attack with our base, we need to think about that resonance stabilization. When we look at the terminal methyl protons, the only way that we can resonance stabilize the molecule is by pushing electrons up this way. However, if we attack the protons on the center carbon, we get resonance stabilization both directions. So we have two possibilities for stabilization as opposed to the one. So that makes the protons on the center carbon more acidic than our methyl protons. Therefore, those are the protons that will more easily be removed. So I'll just get rid of all this. So we're going to focus on those middle carbons, or middle protons, excuse me. We're going to use our basic species to attack the proton, and then this bond between the carbon and the hydrogen is going to move up to the the carbon. And then if we draw out our product, we will get negatively charged carbon plus, and then our sodium counterion, plus the methoxide, which has been protonated, which gives us methanol. So CH3OH, just methanol, is produced. So let's look at the resonance stabilization that we see here. So for the resonance stabilization, we can push this lone pair up and form a carbon-carbon double bond, and we can push one of the carbonyl bonds up to the oxygen to form a negatively charged oxygen. And because oxygen is okay being negative, that is the form that we will see the compound stay in. And because of this, resonance attacking those middle protons is a viable option for the acid-base reaction. And it is the primary reaction that we see. Okay, and let's take a look at one more example. We'll use a base that you most definitely have heard of. So for our acid, we will use benzoic acid. So benzoic acid is just a benzene ring with a carboxylic acid attached to it. And then we will use sodium bicarbonate. And I say bicarbonate because you've all heard of it, that's baking soda. So here we're going to see a similar reaction to the vinegar baking soda reaction. So in order to see the base in the way that we need it for our mechanism, we need to redraw the base. So what this base looks like is we have three oxygens. One's double bonded to the carbon, one is an OH, and then one is negatively charged, balanced by that sodium counterion. So that negatively charged oxygen, just like previously, is going to be attacking our proton on the acid. And then that bond will break and push over lone pairs to the oxygen, just like before. And then we draw our products. And we will get our negatively charged oxygen, which again is balanced by the sodium. Then we get a species that looks like this. However, this is not what you actually get from the reaction. What happens here is this bond between the oxygen and the hydrogen here pushes up to form a new carbon-oxygen bond, which then kicks off the OH group and comes over and attacks this proton. And then what we're left with is actually CO2 plus water. And in most all reactions with sodium bicarb, you always get the negatively charged acid or the conjugate base, and then you'll get CO2 and water as your two byproducts. So those are some of the most common mechanisms that you will see with organic acid-base chemistry. You can use these mechanisms to be applied to all types of different reactions, as long as you understand that the base is deprotonating and you're getting your conjugate base, which is the negative form of your acid, and then some new neutral species after your base has been protonated. That will be your conjugate acid. As long as you understand the flow of electrons from the base to the acid, or to the proton of the acid, you will be able to figure out most, if not all, organic acid-base reactions.